I'm Carlos Azevedo. I work at Ericsson Research. We have a Brazilian branch here at in Indaiatuba, Brazil. And I'm going to talk about a very exciting topic that I'm very excited to be here to share with you is the rise of anticipatory mode objective machine learning, which is something that I really started working when I joined grad school back in 2011, so it's about 6 years now. And I believe there are lots of applications, both in academia and industry, that you can all benefit from, all right? So the material that I based this presentation on is the following. So let me just hide that to make it easy, okay. So we have a paper that we published last year at the IEEE transaction of cybernetics. So I can share the slides afterwards. You can click and read it. Also, I'm based on the thesis that I published in 2014. Also on a position article that I published at LinkedIn. And for those who has this more show me the code kind of attitude, then I have published the code, which is in C++. You can have a look at how these concepts are implemented. It's not magic, so you can have a look and play around with this, okay? Nice. So let me get started by stating the problem that I tried to solve when working on this field. The problem was this: how can we automate mode objective sequential decision-making problems under uncertainty? So let me try to break down each and every word that we're mentioning here. So first of all, the mode objective aspect, we mean that we may have multiple ways of evaluating a decision, okay? And these multiple viewpoints may be in conflict with one another. And by sequential decision-making, I mean that we'll be facing several decision problems over time, and we'll have to output the action at each time step. And by uncertainty, I mean actually two things. First, I mean that the objective functions or the performance criteria that you have may be stochastic or subject to noise. And second, I mean that we may have some missing preferences. So I may not know how to rank given candidate decision based on the set of performance criteria. I may have not defined my preferences a priori, so I may be uncertain about my own set of preferences. So this is the setting that we will do here. And then when dealing with this problem, there are at least 4 challenges, 4 computational and modeling challenges that we need to address. One of them, the first one, is how to cope with such missing and changing preferences over conflicting performance criteria, and try to answer that. Second, how to cope with noisy objective functions. Third, how to measure the quality of future action sets. And finally, how to balance near versus long-term rewards. So all of these 4 questions will be addressed in this presentation, and hopefully you get a sense of the challenges in anticipatory mode objective machine learning. So the best analogy for how this should work, I think, is life itself, okay? So everyone here is alive, I hope so. And in life, we get through several stages, several phases in each, and there are no stopping. They keep coming, and we need to decide, take decisions, and in every stage, our set of conflicting feature goals keep changing. They keep evolving, and we should take decisions. So we should select one action among our action set that keeps only growing, and decide at each stage what should we be doing in order to enable the fulfillment of our future goals, even though we may not know what we would like to accomplish in the future. So it's life, it's really challenging. It really is. So this is only to get a little bit of motivation for this problem. And so in order to deal with such sequential decision-making problems subject to multiple conflicting criteria, we are proposing here to model and work with the concept of anticipatory systems. So what's an anticipatory system? It is a system that is able to simulate possible future states of itself. So the minimum requirement for anticipatory systems is that it might possess an internal predictive model of its own behavior and hopefully a predictive model of its environment as well. And so also have this ability of performing fit-for simulations, you can assess the possible consequences that may happen by taking each and every decision and action that's available to you in the present. And the proposal that we have here is once you're able to generate future scenarios and to assess the consequences of each and every decision that may generate each and every scenario, now you'll be in a good position to reflect on that and try to resolve the arising conflicts that is inherent to all these consequences with our different views of evaluating your future prospects. And so by taking this into consideration, then you have this anticipatory loop right there coming from your predictions to your current state so that you can now integrate this knowledge in your present state and evolve towards your goal, okay? So this is an anticipatory system, and this is what I would like to build. And so in order to build an anticipatory system, I bring here 4 design principles that I try to convey and to follow during my research, and I still do. So the first one is this anticipatory notion that we have already discussed. So the system must learn to simulate meaningful possible future scenarios, and it's able to change the state accordingly. Second, flexibility. So the system should learn to avoid committing to rigid course of actions that cannot be reversed. In other words, we should strive to design systems that keep their future options open, so that you end up with better action sets in the future that will be able to help you in fulfilling your future goals, okay? So third, you should design systems that are self-sustaining, which means that the system should learn how to maintain its short-term value without compromising its long-term value. It's really challenging. And currently in the literature, there are very few works that address this particular issue. And you see in the rest of this presentation that by self-sustainability, I mean the ability of self-tuning the discount factors that arise in the model, in the sequential decision-making model that we're trying to optimize, okay? And finally, we'd like to design systems that that demonstrate conflict resolution abilities, which means that the system is capable of balancing performance trade-offs using the previous design principles. That's why I'm highlighting this box over there, because it really should rely on the 3 other ones. So this is what this presentation today is all about, is how do you get those principles implemented in intelligent systems. So let me show you an example of how such an architecture should look like. So this is the proposal that I've come up with, and I've been experimenting and evolving over time. This is called Anticipatory Mode-Objective Machine Learning Architecture. So let's start explaining it by looking at the lower level layer here. So at the lower level, we have what I call the preferences over multiple stochastic dynamic cost functions, or performance, or objective functions, or whatever you want to call them. So these are simply the objective functions that you are designing the system to optimize. So it might be the case that you have a neural network and you are optimizing it to, I don't know, to minimize the cross entropy among the predictions. So it's a classification task. So this is one objective function. Other objective function might be some regularization term that you have, and you're trying to automatically balance and to solve and to achieve a good trade-off between your regularization terms and your objective function. Or it could be any other high-level objective functions, such as maximizing profitability and minimizing risk, which is the case that for the particular application that I will show you. Okay, so in this layer, you really don't know how to assign a priori preferences. So if I ask you, all of you that are watching this presentation, what is your degree of risk aversion? In other words, how much risk are you willing to tolerate? And to give me a number between 0 and 100%, I'd bet with you that the majority of you will run into problems in estimating the precise number that represents your risk attitude. You know, so because it's subject to many different factors, it depends on your goals, it depends on the current market environment, the political environment, it depends on some psychological factors. So it's a very tricky to input the a priori preferences of the stakeholder of the system and to model that. So we really like to design machine learning systems that are able to work despite not having a clue of what are the precise preferences of the decision makers. Okay, so in order to accomplish that, we can go here to the intermediate layer, which I'm calling a meta preferences layer, in which we can design some meta preferences. So I'm proposing 3 of them. So the first one is preference for flexibility, that is keeping your feature options open. The second one is preference for sustainable long-term predictability. That is, in other words, I'm saying that I'm willing to trade off near-term rewards for the ability of controlling my future environment. So for the ability to have the system being in a predictable environment that it can control. So this sustainable long-term predictability meta preference is just really saying that, hey, I'm trying to keep things under control in the future. So I'm selecting the actions and implementing the actions today that leads to a more predictable future, so I can be better off. Okay. And the third meta preference is the trajectories of minimal historical errors, in which we're saying effectively that we're doing a retrospective assessment of the history of past actions that our system has taken, and you give preferences to types of actions that have shown in the past a good predictable accuracy, you know. So here we're looking to the past performance and rewarding our system on that. So, and if then the problem becomes, okay, I have these meta preferences that I'm claiming that can be used to automate and to define and automatically select preferences in the lower level, but how do we automate now this middle layer? Then what I'm proposing is to go one layer higher to the hyper preferences layer. And this is the concept that I'm calling online anticipatory learning, in which we're trying to control these other 3 meta preferences in a single equation. So each of these preferences that we're learning about here have a precise mathematical definition that I'll show next, okay? So now, when we mix all these concepts together, then the problem becomes, what does it mean to behave optimally in such setting? You know, so we definitely need a model. So let's talk about mathematical models now. So first, let me start by talking about the multi-objective optimization aspects of the problem. So here is the problem formulation. In a multi-objective optimization problem, we are trying to simultaneously maximize several performance functions, F1 to Fm, okay, over a decision vector. And what that implies is that now we have problems in ranking vectors. So we cannot pick 2 random vectors anymore and say that, hey, vector A is better than vector B, unless we define some way of handling with the multiple performance criteria values. And then in this context, the Pareto Dominance is a useful definition, because the Pareto Dominance ranks vectors by contrasting each and every performance value of such vector, and say vector U is only better than vector B if and only if it does no worse than vector B and it's strictly better than vector B in at least one of the criteria. So then you say that U Pareto dominates V. So otherwise, you can't really compare those two solutions, and because one might be better in one criteria, but be worse in the other criteria, and how do you decide which one is better? You can't, unless you have a complete set of a priori preferences. And that's what we're trying to avoid, okay? So in this more objective optimization case, there's the concept of Pareto Optimality. Now, when you're trying to simultaneously minimize F1 and F2, now you run into a barrier, which is known in the literature as the Pareto frontier, or the efficient frontier, which is the geometrical location in this objective space where lie all the optimal trade-offs between your performance functions. And now you can recast your more objective problem as the problem of populating this Pareto frontier with a finite approximation. But then the problem becomes, how do I decide which approximation is better, this one or this one? You know, because now there are an infinite number of possibilities to populate this frontier, and I can't distinguish among them. And so here is where the concept of hypervolume optimization becomes handy. Now we are going to define an objective function over sets, and now we have a set-based formulation problem in which the goal is to find a finite set of decision vectors of whatever decision you are trying to come up with that maximizes the hypervolume, which simply measures the area of the dominance, of the union of the dominance regions of even each and every decision. So all this region behind Z2 lie points whose performance is Pareto dominated by Z2. And when you perform the union of those regions and compute the area, then you have a means of progress, of measure progress in this problem. And now you can say that this is the distribution that maximizes the hypervolume, then this is preferable in the more objective optimization sense. So this is the performance function that we're going to use. And this is the metric. Don't worry very much about the mathematical formulation. But now let me try to explain you and to justify why we are selecting the hypervolume for this particular model. So the hypervolume, it refines the Pareto dominance. So the Pareto dominance is the dominance that I just showed to you. And there are known results in the literature showing that the hypervolume, whenever I add some point that's non-dominated to my set of non-dominated, Pareto non-dominated points, then its hypervolume, the hypervolume of the set should increase. And this is a nice property of the hypervolume. Another nice property is that when I maximize the hypervolume over an infinite number of points, then I actually recover the Pareto frontier. So we have theoretical guarantees that that lead us to nice results. So the reason here is that the set-based Pareto dominance satisfies a concept in the literature that is known as flexibility consistency, which says that a decision maker should prefer to augment its set of options whenever this option that you are adding to your options, to your action set, is not dominated by any other option that was originally there. So if this is the case, then you have some flexibility consistency, and you are being consistent with the notion of keeping your options open. And so since the hypervolume refines the Pareto dominance, then we can conclude that hypervolume is in itself consistent with this notion of preference for flexibility. Okay, so if you want to design systems, machine learning systems that will keep options open, then it's a good idea to select the hypervolume as the cost function. This is a nice result that this kind of research can assert. Okay. All right. So now it's not enough that we are now able to use the hypervolume, because now we should deal with the fact that our performance functions might be stochastic. So say you are training a neural network and you are using something like the stochastic gradient descent, or some other training techniques such as k-fold cross-validation, which means that whenever you're training your model, you get some error that essentially is a random variable, because you're randomly selecting examples for training sets. And you do that because you want to have some generalization properties in your model. But that brings about the difficulty that now, whenever you test your model, you may get a different performance. So if you look at your objective space, you see that the performance of your model now can be modeled as a distribution. So in this case, I'm trying to fit two bivariate Gaussians to these two models, U1 and U2. Okay, and now what that implies is that the hypervolume, the measured hypervolume in itself, it will be also a random variable. So how can we deal with that? So let me show you the concept of a stochastic Pareto frontier. So this is a stochastic Pareto frontier that I've computed for a financial portfolio selection problem using real-world data from the Dow Jones Index. Okay, so I composed a set of portfolios. I've optimized those portfolios, trying to simultaneously maximize the return and to minimize risk. And when I did hypervolume-based optimization on that, I arrived in these results. So when I performed sampling, a Monte Carlo sampling of all the possible scenarios that the stock markets could evolve into, so we get those kinds of distributions that models very well. The orientation here varies as I walk through each and every possible portfolio. So for the top right level portfolio, you see that this is the guy that is the most uncertain one, which has a higher spread, okay, in this distribution. So there are other portfolios that yields a lower return and lower risk, that are more well-behaved despite of the behavior of the market, despite of the scenarios that I'm simulating. So yeah, so you see that the stochastic Pareto frontier in this sense, it's give us a nice way of reasoning over uncertainty and to select solutions based on the measure of uncertainty that we have over multiple conflicting scenarios. So this is an example of what you can do. But let's remember that our problem is not only mode objective and stochastic, it's also a mode stage. So we want to perform anticipation. So now, suppose that we are on time t, and I have these two candidate solutions, U1 and U2, that I could implement in my operating environment. But the problem here is to decide which one should I implement, okay? So if I take U1, I can modify my problem in such a way, because I may incur in transaction costs. I may, I don't know, I may modify my environment. This action that I select might prompt some adversary, if it's the case of a board game, such as Go, to select another strategy that completely modifies my future performance. So I'd end up with a completely different problem in the future. And on the other hand, if I select U2, I can have a completely different problem. So now you see that by allowing time to evolve in a more objective problem, we run into this dilemma, which is, how can I make any sensible decision in this scenario, since I'm modifying my problem and if I don't have any a priori defined preferences? So effectively, what we're doing is to explore this Pareto tree, in which each node is a set of Pareto optimal functions, and we are trying to, at each node, try to decide which options should be implemented, and that will determine the kind of a future Pareto set that is achievable. Okay, so it's a really challenging problem. So we need to find a way to deal with that. And so again, I would defend that we should use hypervolume decision making over time. So we should, I will argue here that we should maximize the sum of hypervolume over time. So intuitively, suppose that I'm here solving, say, a financial portfolio optimization problem, which each and every point is a different investment that I make in different risky assets in the stock options market, for instance. So I can measure return and can measure risk. And if I'm a very risk-prone investor, I can decide to, at each decision stage, to implement the most risky option, which is predicted to yield higher returns. The problem, if I do that, is that in the long run, this greedy strategy might not be the one that will keep my future options open. So by the time that I arrive in the decision stage T6, I may have worse options, which means that the hypervolume that's available to me in my action set in the future decision stage T equals 6 may be lower than another kind of a decision-making strategy. So what happens if by the time that I arrive in the decision stage 6, I change my preferences? So I realize that I won't have any really good, less risky, more conservative portfolio to play with, because the cost would be prohibitive. So what I propose instead is that you can automate this kind of decisions. So instead of going into for a fixed preference, for a fixed relation on which portfolio that is available to you, you should decide and pick and decide in each stage, you should flexibilize that. And you should select the portfolio that is predicted to maximize the sum of future hypervolume over time, and hopefully in the situation below in option B, you can flexibilize this and have the option of, if you want to, at decision time equals 6, to make a more profitable decision in terms of investment. Okay, so here is the reasoning on how hypervolume decision making over time is justifiable. All right, so in order to implement this concept, we've come up with some models. Okay, I call them online anticipatory stochastic mode objective optimization models. I'm not getting into too much details here, but basically we have a solver, which is a metaheuristic that implements some predictive Bayesian models internally to predict its own future state and to track future sets of Pareto optimal solutions. And from that predicted future optimal sets of Pareto solutions, then we input that set to the S-metric maximizer. S-metric is another name for the hypervolume, in which we should select the decision that is predicted to improve your future hypervolume. So you play around with this in the right side. I call all of these components in the left side as the Osmo solver, and you just unfold this solver over time. And so you have a kind of online decision-making strategy in which you are accumulating scenarios, input scenarios. So you're basically accumulating data and trying to improve your predictive models based on the accumulated data in the past, and just solving a sequence of anticipatory stochastic mode objective optimization problems over time, using this very same strategy of hypervolume maximization. Okay, so obviously I won't show you the precise equations because they don't matter right now, but this is the predictive solution of the Osmo problem, in which basically now we are trying to find the solution U of t star that maximizes the expected value of the S metric, which is the hypervolume, over this weighted sum of all pairwise solutions contained in a trade-off set Z hat, which is predicted to be achieved in the future in a stage t plus h, where h is my prediction horizon, given that I have taken the decision u at time t. Okay, so it's a kind of a conditional based feed-forward simulation that we are doing. And we are averaging this with those lambda factors here, lambda, which is indexed by t plus h, which are called the anticipatory factors. All right. And so, as I mentioned to you in the beginning of this presentation, I'll show you some strategies to automatically tune these lambda parameters. Okay. So we are finally arriving this anticipatory mode objective learning concept. So here we are seeing an objective space composed of a variance, which is the risk, and me, which is the mean of the investments. So now I'm taking this portfolio optimization application as an example. And here I have the predicted performance vectors associated with a particular portfolio investment. And I try to track that using a Kalman filter over time in the objective space. So I'm trying to track these distributions. And by the time I arrive at the present moment t, I just do the forward step, which gives me the predictive distribution of the Kalman filter. I'm using a linear dynamic model. You can find more details in the paper, it doesn't matter. But basically, I'll get a prediction. And what I do with this prediction is that I try to perform a convex combination between the predictive distribution with my current estimated distribution of my performance vector for each particular portfolio. Okay, so arrive at this update equation right here, in which you see that it's just this convex combination between the predictive distribution and my current estimate, okay, which are Gaussian. So there are nice ways to perform convex combinations between Gaussians. Essentially, you'll be combining them over the parameters, over the mean vectors and over the covariance matrices. All right. So in order to automatically set up lambda, which is my anticipation factor, which really controls the extent to which I'm willing to trade off near-term performance for long-term performance, there are two other meta preferences that I told you. The first one is the preference for decision trajectories of minimal historical error. So in this case, what I do is I get all the historical residuals of the Kalman filter application, which is trying to track and correct the distributions over the whole history or of the data stream that I have, of evaluating my investment, my portfolio on historical market scenarios. Okay, so I get those errors, and what I do is that I get the current error of the current distribution and normalize that by the difference between the maximum and the minimum error in the historical set. And by doing that, I have a nice heuristic to set up lambda. Okay, so lambda will be independently set for each time step and for each performance distribution that you have in your Pareto set. So based on this, how well your predictive model performed for each portfolio and in which historical scenarios. So once the reasoning of this equation is once your normalized historical squared residual is low, then you are going for long-term performance. Whenever this quantity is high, then you are preferring near-term performance, which makes sense. And here is how do you perform this, how do you compute your anticipatory distribution, which is a complex combination of your predictive distribution and your current estimation. So it's just a complex combination over the parameters using these anticipatory factors, which are automatically determined from data, from your historical error measurements. Another strategy to automatically turn lambda is instead of looking at your error trajectories in the past, why not looking at your actual predictions in the future? So this is a preference for long-term predictability. So what I do is that I measure the entropy of temporal Pareto Dominance probability. So I compare the predictive distribution with my current estimate and say, okay, what is the probability that my predictive distribution will Pareto dominate my current distribution, my current performance? So by using the Pareto dominance, I'm being agnostic with regards to the user preferences. So I'm not really taking user preferences into account. And I'm also measure the uncertainty over this Pareto-based relation, which is really the key that makes the hypervolume maximization work. So it's a nice way of measuring the uncertainty that we have about whether we'll be better off or not in the future when you consider this agnostic view over preferences. So the reason here is that we get 1 minus this entropy of the temporal Pareto domination probability, and whenever this entropy is low, we aim for near-term performance. Whenever it's high, we aim for long-term performance. So here's the algorithm. So we really try to predict and track and use all those strategies in some nice ways. I won't get into much details here. And then another thing that we can do is, okay, I should be able to compute the expected value of the hypervolume contribution of each candidate solution in the objective space, so that I can use this quantity as an informative quantity for designing heuristics, search heuristics, to know which portfolios or each candidate solution should I remove from my set of candidate solutions, and which ones should I add. Okay, so there's a nice way, once you model these as a bivariate Gaussian distributions, to arrive at this quantity, and then you can design nice hill climbing heuristics to maximize hypervolume over time. All right, so let me, to finalize, talk a little bit more about the results of the portfolio selection application of this framework, okay? So as I have hinted to you before, we are using some multi-causal simulation in which we try to model the data that we have of the stock prices of the return processes that we have for each and every financial asset. And we're trying to simulate plausible scenarios to measure the performance of our candidate investments, okay, in terms of return and risk. So, and we are trying to simultaneously minimize risk while maximizing a cost-adjusted return based on some transaction cost functions. Now, this is the result that you see when we apply this algorithm. So here is the stochastic Pareto frontier evolving over time. So for different time horizons in some simulated markets. So it's very nice. You can see that as time goes by, the volume, if you were able to measure that computed over these performance distributions, are clearly getting higher and higher. So which means that our hypervolume maximization over time is really working. And it is also working, taking into account all the costs and the noise measurements. Okay. All right, so this is a very nice result. We can measure what's going on with the anticipatory factors, which are lambdas, for each and every portfolio that we can rank according to risk. So a portfolio of ranking 1 means that it's the most risky portfolio of my Pareto sets. and a portfolio of rank 20 is the less risky, and also it will result in less returns as well. So here I'm measuring the confidence, which is 1 minus lambda, 1 minus the entropy of the temporal incomparability probability that I'm measuring. And you see that when this is the results that I get for the Dow Jones Index. I'm trying to evolve portfolios there. And you can see that the confidence of the most risk portfolios are generally higher than the less risk ones when we are not looking very much into the past. So K equals 1 means that we are using just the previous market state. So it's a very short data window that we are using here. Whenever I start to look more into the past, so I increase my window size, then you can see that this situation completely is inverted, is reversed. So now I'm more confident that the less risky portfolios will yield more predictable future performance. So suddenly, by just changing one parameter, by adding more data into my data stream, the behavior of the algorithm completely changes, which is very, very interesting. Here is the results that we get when we measure the hypervolume, the future hypervolume that is predicted to be achievable if we implement the portfolios, the investments, which are ranked from 1 to 20. So we have 20 portfolios, candidate portfolios that we can implement, sell and buy and modify our portfolios in which and every decision stage. So here you can see that the most risky portfolios were the ones that we were predicting the best hypervolume for the Dow Jones Index when we were not using prediction at all. K equals 0 means that we are just assuming the market to be static, which is absurd, but anyway. And when we turn prediction on and start using some past market condition environments to try to predict some quantities, then we can see again this change of phase of in the behavior of the algorithm. Now the algorithm is much more likely to select less risky portfolios. And what it means in terms of your accumulated wealth, that is what it means in the end, is that over several simulated markets, Dow Jones, London market, Hong Kong market, you see that by turning prediction on, using the right predictive model, and by selecting the hypervolume-based decision-making strategy, you can beat several other strategies which doesn't use prediction and which try to be greedy in the kind of portfolio that tries to implement. So you're always selecting the portfolio that you think that would yield higher returns. Okay, so it's quite amazing. And these periods over here are actually around 2008, 2009, the period of during the big financial crisis. So you can see that we still end up losing some money, but not as much as other strategies. And when it comes to markets, financial markets, this is already a very good result. Okay, and to finalize our discussion, so I'd like to point out that this kind of strategies that are presented here today are very similar to the work of Wissner-Gross of causal entropic forces. Okay, so in 2013 he proposed an equation for intelligence, and he viewed intelligence as a physical process that tries to maximize future freedom of action and avoid constraints in its own future. So yeah, so basically we are following this very same philosophy here, but instead of maximizing our future entropy of the microstates that our system can be at in the future, we are imposing some objective functions that are able to measure and to rank the most preferred future states, which conveys a way for you to really control the evolution of the system. Okay, so this can be an interesting building block for intelligence. So I apologize that this ended up taking more time than predicted due to some technical problems. And I hope that you enjoyed this presentation. And now I'd like to open up for some, hopefully for some questions, okay? Okay, so Joshua, you are asking, are you trying to program judgments? Yeah, in a way. So Benjamin Franklin once famously said that the most important decision that a human being can make is to select its own value system. This is the single most the single most important decision that you can have in your life. So in a way, what I'm claiming is that once you select the right objective functions and you design your meta preferences in a way that can automate and balance your different set of value functions that you have, then in some sort of reasonable way, then you might be able to construct some more intelligent system that does not require some offline fine-tuning when it comes to a priori specification of preferences and to some other parameters. Okay, so imagine also that instead of a portfolio of financial investments, I could have a portfolio of algorithms, and I could measure the training error of such and such algorithms over time, and also the risk in such and such scenarios. And so I could use that to automate the allocation of computational resources into this portfolio of algorithms. So yeah, you can use this kind of frameworks for many kinds of judgments. Yeah. So Joshua, you have a second question, if this is applicable for warfare. Well, that's I have not envisioned any warfare applications for that. If you compare to the work of Wissner-Gross that published in 2013 on causal entropic forces, he certainly envisioned that, since he demonstrated how this principle could solve strategic decision making when it comes to positioning battleships to maximize coverage of the global territory for military strategic reasons. So yeah, I'm assuming that you could use hypervolume maximization over time for the same purposes. So in the end of the day, I think is up to your to the ethical values of the designers to apply these kinds of technologies to one case or another. So yeah, I don't see any reasons why this could be adapted to warfare, but I hope it's not. It's a bit complex for me, Alex is saying. Look forward to studying the material again. And the final question, what are the challenges that come along with anticipatory machine learning? Okay, thanks for your comments, Alex. I know that's a bit complicated, so I hope you can get access to the material before, and just drop me an email if you have any doubts. But when it comes to the challenges, I definitely see some modeling challenges, because the kind of predictive models that you have are still very much problem specific. So in my case, the portfolio selection case, I had to come up with some common filters for tracking performance in the objective space. I had to design some dynamic Dirichlet processes in the decision space. I have not mentioned that, but which are specific for the representation that I used of the portfolios, which is a simplex space. And I was tracking Dirichlet distributions over time. So I think the biggest challenge for this kind of applications is how do you automate the predictive modeling part. So hopefully we can handle that with neural networks, since neural networks can learn arbitrary functions and do not require many modeling assumptions a priori. So I think, yeah, I think this is one big challenge, and I hope that we can come up with clever ways of do not be problem specific. Okay. Okay. So thank you very much, Alexa. Thank you, everyone, and see you next time. Take care.